Okay, in this video, we're going to look at aerobic respiration, and particularly we're going to look at one aspect of it, which is called glycolysis. And if we look at a cell, we know we have a cytosol or cytoplasm, and this is where glycolysis occurs. And then you have a mitochondrion, and this is where pyruvate decarboxylation and the citric acid cycle occur. And of note as well, in glycolysis, glucose is converted into pyruvate and it produces some ATP, or at least there's a net production of ATP, um, because some is used up to begin with. And glycolysis also produces NADH, and this is going to be involved in oxidative phosphorylation by the electron transport chain and by chemiosmosis. So it's in a sense similar to what happens in photosynthesis, except the energy doesn't come from light, it comes from chemicals. And this is where most of the ATP is made. But as I said, today we're going to be looking at glycolysis. And the steps are these. Explain the sequence of steps in glycolysis. And we're going to look at it as a stepwise breakdown of glucose in cellular respiration. We're not going to look at the names of the enzymes. Well, it'd be nice to know them, but it's not going to be required for the examination. And includes the initial phosphorylation of glucose, lysis into 2 or 3 carbon compounds, and the subsequent production of pyruvate, and a small yield of ATP and reduced NAD, and recognition of simplified structure and formula of the intermediates. So notice a simplified structure. So, as I said earlier, glycolysis, well, first respiration occurs in 3 parts. You have glycolysis, which occurs in the cytoplasm, and it occurs in all living cells, both prokaryotic and eukaryotic. Then you have anaerobic respiration. This occurs in the cytoplasm as well, where oxygen levels are low. You have aerobic respiration occurs in the mitochondrion, where oxygen levels are normal. And the aerobic involves Krebs cycle and pyruvate decarboxylation. But we're going to look at glycolysis, which occurs in several steps. So we have glucose, and notice glucose is what is called a hexose sugar. Well, it has a pyranose ring. It has a hexagonal ring. Um, and glucose is converted into glucose 6-phosphate. And importantly, this takes up an ATP molecule. So ATP is converted into ADP. The importance of this step is that glucose 6-phosphate can no longer leave the cell. Once you phosphorylate it, it becomes positively charged, and therefore it can't pass through the cell membrane. And there are no specialized carriers to allow it to leave. So once we phosphorylate glucose from glucose 6-phosphate, the molecule can't leave the cell, but glucose molecules can still enter. And then glucose 6-phosphate is converted into fructose 6-phosphate. And this is a furanose ring. It's pentagonal shaped, and it is more symmetrical than glucose, and therefore it's going to split more easily. And glucose 6-phosphate is converted to fructose 1,6 bisphosphate. So we phosphorylate it again. And this is the rate limiting step of glycolysis. It's basically, if you remember from chemistry, the rate limiting step is the slowest step. And this reaction is really the rate is dependent on the concentration of ADP. If concentrations of ADP are high, then the rate occurs fairly quickly. If the concentration, and if the concentrations of ADP are fairly low, the reaction occurs much more slowly. The point here being if concentrations of ADP are high, it means ATP is being used up fast, and therefore there's a greater demand for ATP production. If ADP concentrations are high, are low, this means that you have a lot of ATP present, and it's not being needed as much because it's not getting used up. And the importance of the molecule being symmetrical is it now splits into two 3-carbon atom compounds. You have dihydroxyacetone phosphate and glyceraldehyde phosphate. And the dihydroxyacetone phosphate can be converted into phosphoglyceraldehyde. Because the aldehyde is going to be converted into an acid. Notice converting an aldehyde into an acid is an oxidation reaction. So you need some unoxidizing agent, and the oxidizing agent gets reduced. And the oxidizing agent is NAD+, which gets reduced to NADH. And NAD is nicotinamide adenine dinucleotide. Similar to what you have in photosynthesis. Although in photosynthesis you have NADP+. So there's a slight difference. And at the same time, when you oxidize the aldehyde to an acid, we also add inorganic phosphate. So the molecule now has two phosphate molecules associated with it. And the phosphate can be used to form ATP by something called substrate level phosphorylation. So ADP is converted into ATP. And then after a further series of reactions, the other phosphate molecule comes up to produce ATP, and again in substrate level phosphorylation. The production of the ATP and the ATP here are important. And notice, since the molecule has turned into the 6-carbon compound, has turned into two 3-carbon atom compounds, there's a net production, so there's an overall production of 4 ATPs altogether, because each one of these produced one. So you have 4, but 2 of them are used up. So overall, there's a net production of two ATPs, and the NADH is going to go into the Krebs site and to go into the mitochondria, where it produces ATP by oxidative phosphorylation, a process we'll look at later on. So this more or less states what happens in glycolysis. To put words to that diagram. In the first step, glucose molecule is phosphorylated. This reaction requires ATP, so it uses up energy. That's this process. This reaction is important because it prevents a glucose molecule from diffusing out of the cell, and more molecules can enter. So glucose can enter, but can't leave. It also makes the molecule more reactive. In the second step, glucose is converted into fructose. This makes the molecule more symmetrical, so that it can split more easily. This molecule is more symmetrical than this one, and therefore splitting it becomes more easy. So the molecule is then phosphorylated a second time. This is a rate-limiting reaction, and it occurs readily when ADP levels are high, and gradually when ADP molecules are low. And if ADP levels are high, that means that ATP is being used up quickly, and therefore there's a higher demand for ATP. Hence, the rate of glycolysis slows down when ATP requirements are low, and it speeds up when ATP requirements are high. And it also further activates the molecule, so it will split more readily. Okay, the molecule now splits into two 3-carbon atom molecules, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. And dihydroxyacetone phosphate needs to be converted into glyceraldehyde 3-phosphate. The reason for this is that aldehydes can be oxidized, but ketones cannot. So glyceraldehyde 3-phosphate is then oxidized to 3-phosphoglycerate, and this is an oxidation reaction and occurs in the process. NAD plus is reduced to NADH. And I said, note this reaction is opposite of photosynthesis. Only NADH is involved rather than NADPH. So 3-phosphoglycerate is then phosphorylated into phosphoenol glycerate. This reaction does not require ATP, since the phosphate is inorganic. So if you notice here we have inorganic phosphate entering, whereas here you had ATP being used up. So this step, when you're phosphorylating the organic compound, doesn't require energy in the same way that this one does. So is then phosphoglycerate. The reaction does not require ATP since phosphate is organic. And this phosphoglycerate is then reacts to form phosphoenol pyruvate. At this step, ATP molecule is generated by substrate level phosphorylation. So it also have substrate level phosphorylation. And phosphoenol pyruvate reacts to form pyruvic acid, generating a next molecule that is generated by substrate level phosphorylation. So from this point, we can go to this point where again ATP is being generated by substrate level phosphorylation. I think probably learning all of these intermediates here isn't that important, but you ought to know this one. You ought to know this one, because those are important. you need to know the splitting of the glucose into two three-carbon atom compounds, and that an aldehyde is formed. And the aldehyde can be oxidized to an acid, and in this process, NADH is produced. And then you have inorganic phosphate coming in, and therefore the molecule now has two phosphate groups and can produce two molecules of ATP by substrate level phosphorylation. And this illustrates substrate level phosphorylation. When you have a substrate, such as phosphoenol pyruvate, and you have adenosine diphosphate, and it can combine to form ATP and pyruvate, and this is substrate level phosphorylation. So in substrate level phosphorylation, phosphate from an originally inorganic source is added directly to an ADP precursor to form ATP molecule. In glycolysis, only a few ATP molecules are produced this way. Most ATP is produced by oxidative phosphorylation. As we will see, it's from an originally inorganic source. Notice this phosphate is really organic phosphate, but this phosphate here came from an inorganic source, not from a ATP. So that's why it's originally inorganic. Note that in glycolysis, two ATP molecules are used up and four ATP molecules are produced. So there's a net gain of two ATP molecules. And that basically completes this talk on glycolysis.